So now we're going to talk about some properties of these matrix operations that we've just defined. And ultimately, these properties are what makes these matrix operations so useful. These properties are what turn matrix operations into a matrix algebra. And algebra is a powerful tool because of the fact that it's flexible and has these different ways of manipulating and rewriting the things that we're interested, expressions that we're interested in. So these properties are a big deal. The first one I'm going to note is what you might call an associative property. This is the associative property of matrix multiplication. This one is actually not so easy to prove, at least not so easy to get a good sense of how to prove, how to see why this ought to be true. At this point in the course. It's going to turn out that it's going to be much easier once we understand this idea of linear transformations, and it turns out that this is one of these applications that we've talked about previously. From the point of view of linear transformations, this is a very natural thing to understand. As of the moment, of course, we don't know what those are, and so I'm going to skip the proof of this fact, this associativity fact, and prove it later when we have better tools to work with. You can prove this. The book gives a proof of this using sigma notation, and it works, but it is cryptic. It's not intuitive. It's hard to look at that proof and get an intuition of why this really ought to be true. Okay. This is what you might call a distributivity property, and this is a what you might call a scalar associativity property, because again, you can move the parentheses about involving a scalar multiplication in the mix. So these two properties, again, they look pretty good on the page, seem like they might be reasonable. These you can go ahead and prove now. You have all the tools at your disposal to be able to do those proofs. Those would be good exercises, things to work out for yourself. So for example, the way you'd go about proving this fact is just use what you know about how to add two matrices. So for example, what could you say about one of the columns of B plus C? Right? And then ask yourself how you would make use of that in this matrix multiplication. And then likewise, what do you know about these matrix multiplications, and what can you say about how to add? So it turns out it's not hard to show that these are exactly the same thing. There's different points of view that you can take, different approaches of ultimately proving the same thing, but you certainly have some options, and you can give those a try now. Okay. All right, some definitions, objects of interest. The zero matrix. Pretty clear why we call this the zero matrix. It's made up of entirely zeros. We need to distinguish the zero matrix of different shapes, so we'll note here that this is the M by N zero matrix, because it has M rows and N columns. Now, less clear is why we call this the identity matrix. It turns out, now you'll notice, by the way, that this has got to be square. Same number of rows and columns. So there's only need for one subscript here, indicating how many rows and columns. Turns out that this matrix has some interesting properties, as does the zero matrix. Now, the zero matrix has some really easy to see properties right there. This is something you can certainly prove on your own. It's pretty self-evident, so I won't spend any time talking about that. But this identity matrix, oddly, has the feature that you can multiply it by any matrix of appropriate dimensions, and you get the same matrix back. And furthermore, you can do it on either side. So this matrix, in a multiplicative sense, behaves kind of sort of like a 1 in some sense, right? At least in terms of multiplication. So not obvious why this would work, and sort of weird that you'd have 1s on the diagonal and zeros everywhere else, but it turns out to be exactly what you need. Okay, so I'm going to walk you through why this works. In particular, I'm going to walk us through this discussion here. Why is it that left multiplying by the identity doesn't change a matrix? All right. Well, now you'll notice that this is the M by M identity. So per matrix multiplication rules, I need to have M rows in my matrix A for this to be a fair multiplication. And now let's do this multiplication. I'm going to do this multiplication one row at a time. How? So, for example, would I compute, let's say, the ith row of this product? How would I compute that ith row? Well, let's take a linear combination of rows point of view. Right? That ith row is going to be a linear combination of these rows, where I use the corresponding row, that is here the ith row, as my coefficients. Right? Okay, well, now, fine, so I've got a linear combination. Now, good news, in this ith row, there's mostly a bunch of zeros. Right? Lots and lots of zeros in here. Now, there is a 1 on the diagonal, but then after that, a bunch of zeros. So, in fact, this linear combination, I'm taking, this linear combination of those rows, that linear combination, all of the terms are going to go away except for a single term, because in all of the terms except for one, the coefficients are 0. So, which term is it, though, that doesn't go away? Well, the term that doesn't go away is the term where the entry is 1. Now, which one is that? Well, we're in the ith row, and we're looking on the diagonal. The diagonal is where the row number is equal to the column number. And the column number says which entry we are. So, in particular, then, in the ith row, it is the ith entry that has a 1 in it and not a 0. Okay. All right, so let's remind ourselves what we have then is this linear combination of those rows, but we've just agreed that all of the terms go away. All the terms go away except for one of them. Right, the one term that doesn't go away is the ith term. That ith term comes from, let's see here, multiplied by the ith row there. And so what I get there is AI. So, long and the short of it, what I've done is I've shown, get rid of all this mess, what I've shown is that in this product, the ith row of the product is exactly the ith row of the original matrix. And this is true for all values of I. So, for example, the first row is the first row of the original matrix. The second row is the second row of the original matrix, etc. And so, in fact, the product is this original matrix. This product is exactly that matrix. Okay, so it's nice to see how this is an immediate consequence of matrix multiplication, but you can see furthermore how this makes explicit use of the linear combinations of rows point of view of matrix multiplication. The dot product point of view is not clear how that would be as useful. Okay. Now, I'm going to, again, give you another recommended exercise. I think this would be great practice. Try to make an analogous argument for this fact. Why is it that if you multiply with the identity on the right, that this still continues to be true, that the matrix doesn't change? It's again going to be a linear combination argument. It's just that in this case, it's going to be a linear combination of columns argument. So it's going to be analogous, very analogous to the argument we just walked through. Corresponding changes, of course, but with columns instead of rows. Okay, nice practice problem exercise for you guys. Okay, here's another, there's a nice application of matrix multiplication. And recall, of course, that we've been interested since the first day of class in solving systems of equations, among other things. So we had a shorthand for how to represent a system of equations. That was to just sort of lift these entries, the various coefficients and the constants on the right hand side would just lift those up and make a matrix out of them. Right, and that was a shorthand. Put a line there for where the equals are. That gave us a shorthand representing a system of equations. All right, so what I'm about to show you is another way to use matrices to represent a system of equations as a kind of a shorthand. And it's based on matrix multiplication. So again, I'm going to take the same coefficient matrix that we did previously, right? Call that A, just as we did in the previous section. We're going to take the numbers on the right-hand side, well, just the numbers on the right-hand side, and make a column vector out of them. And then these numbers that I'm looking for, x1, x2, etc., xn, those numbers, I'm going to make a vector out of them. And having done so, let's consider what is AX. What happens when I multiply that times that? Well, let's see here. If I multiply A times X, this matrix times this column, kind of a, I guess you could say it's a matrix. Let's use the dot product point of view. The first entry is going to be that dot that, which is that exactly. The second entry is going to be that dot the exact same thing, which is going to be the second, the left-hand side of the second equation, etc. So dot 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 that dot that can give me the last left-hand side. So interestingly, turns out that AX, this product, A times X, gives me exactly the left side of the equation. Weird. How about that? Of course, B is the right side of the equation. And so, wonderfully conveniently, this one single equation, AX equals B, by itself represents this entire system. The left-hand side is AX, the right-hand side is B. So it's very convenient shorthand. Now, of course, you might be thinking, look, we already had a shorthand. Right? We already had augmented matrices. Why do I need to write it with matrix multiplication? What does this buy me? Well, there is something huge that this buys us, and in particular, we have properties of matrix multiplication. Matrix multiplication, matrix addition, these sorts of things, that's not just operations that we've written down. They're operations that have properties. It's an algebra. We can do algebra with matrix multiplication. So this is not just a shorthand. This is a shorthand with the potential for being able to use algebraic manipulations to do some exploring and come up with some good ideas. And that's exactly what's going to happen, in fact, on the next page. Okay. So here's the theorem that we're going to prove. It takes a couple of minutes to express what this theorem is actually saying, and then we're going to prove the theorem as well. So let's see here. We can, let me zoom in one notch. We'll have a little bit more room. So suppose you have a system of equations, and there you'll notice is the matrix shorthand for the matrix multiplication shorthand, in fact, for a system of equations. And let's suppose that I have a solution. I'm going to call this solution XP, P for particular. So all that means is that this is a specific solution to that system, and I'm going to fix it. There's nothing magic about this solution. It's not a solution in a way that other x's aren't. It's just a solution, but I have to decide what it is and stick to it. Not allowed to change for the purposes of this discussion. Okay, so we're going to stick to that one particular solution. What the theorem says here is that finding a solution, so any solution, whatever this other solution might be, that is synonymous with this equation, namely that this other solution that you found is exactly your particular solution that you've already specified, plus some what we call homogeneous solution. Now let me talk for a moment about what do we mean by a homogeneous solution. Well, a homogeneous solution is just a solution to the corresponding homogeneous equation. Remember, homogeneous means 0 on the right-hand side. Right? So this AX equals 0. This AX equals 0 is the corresponding homogeneous equation. It's got the same coefficient matrix, just zeros for the constants instead of B. Okay, so again, what this theorem is saying, this is an if and only if. So it's saying that the following two statements are equivalent. It's saying that being a solution is always simultaneous with being of this form. All right. Now I emphasize this means two things. It means whenever you have a solution, it means that that solution can be written as xp plus xh. But it also means that if you have something of this form, xp plus xh, it means that that's a solution. So we actually have to prove both of these statements in order to prove this theorem. So we'll take these one at a time. All right. Yeah. Okay, so we're going to start off doing this. I'm going to start off by assuming that x is xp plus xh, where p is our particular solution. Excuse me, xp is our particular solution, and xh is a homogeneous solution. So we're assuming that. All right, now our goal that we're trying to prove is that x is a solution. So we have to ask, how do I know if x is a solution to the original system, ax equals b? Well, the way I'm going to check to see if x is a solution is I'm going to compute ax, and I'm going to, fingers crossed, hope that I get b. Now, of course, you can look ahead and see that sure enough we are going to. Okay, so I'm just going to directly compute this ax. All right. Well, ax, don't forget that x is xp plus xh. Right, that's what we're assuming. And that allows me to write this down, and here's our first instance where we're in fact using our not just matrix multiplication, but we're using our properties of matrix multiplication. We're using the fact that this is an algebra, and then I can manipulate these things by using the distributive property here. Okay. All right, well now let's analyze what are these two things. Well, don't forget, by assumption, xp is a particular solution, and that means it's a solution to ax equals b, and that means that axp equals b. That's just by assumption of what xp is. What is axh? Well, remember, our assumption is that xh is a solution to ax equals 0, and that means that axh is 0. Right? That's just by assumption of what xh must be. Altogether, then, I have b plus 0, and that's b. So what I've confirmed is that ax must equal to b. I made a wrong color choice there. Ax is equal to b, and so sure enough, x is a solution. Okay. Right, so I have confirmed that it goes this way, that this does indeed imply that. And now we have to go the other way. Now we have to assume we have a solution and ask, does that necessarily mean that that solution x is of this form? Need it necessarily be xp plus xh, where p is our particular solution and xh is some homogeneous solution? Okay. All right. Well, suppose x is a solution. Well, this is our, again, that's our assumption. We get to start off with x being a solution. And Now this is a little bit of a bank shot, mathematical bank shot I like to call it. So we're going to get to the conclusion we want, but we're going to get there by way of looking at something that does not immediately seem relevant. And for the moment it's not clear why this is going to be relevant. Turns out that it's going to be. So for the moment we have to take it on faith. This is actually going to give us something that we're interested in. So tricky part of the proof. So we're going to start by computing this for no particularly apparent reason at the moment. Okay, well, step one, distributive property. So again, this here we're taking advantage of the fact that this matrix multiplication is not just a shorthand. It's not just operations that I can apply following certain arbitrary rules. These are operations that have properties. Namely, I have an algebra, and this is where I make a big use of it right here. Now again, what do I know about these things? Well, by assumption, x is a solution. Oops. By assumption, x is a solution, and therefore ax is b. But don't forget about the fact that by assumption, for the purposes of this whole problem, xp, being a particular solution, is a solution. So axp, also b. And that means that I have b minus b, which of course is 0. Now, so what? This object that I'm not clear why I care about is equal to 0. And what does that buy me? Well, what that buys me, what that tells me, is that this x minus xp, I guess I did this in purple, this thing, x minus xp, that's a homogeneous solution. Because you can see right here, that thing, x minus xp, when you multiply it by a, gives you 0. That's the definition of a homogeneous solution. So I'm going to choose then to call that xh, and then as required, I started off by assuming that I had a solution x, and I have now shown that x is xp plus xh. Okay, so that as desired, I've shown that. Okay, so neat fact, this one solution, this one xp thing, this particular solution, that gives you a relationship between all solutions to the original system you're interested in and homogeneous solutions, namely solutions to this related homogeneous system. So it's a really interesting fact. Now, question, is this computationally useful? Well, it's not clear. But I want to remind you, that's not our only goal. Again, our goal in this class is not to come up with things that will help us do arithmetic more conveniently. We want to see relationships between different ideas, and certainly this does that, right? We've found that the solutions to that equation and the solutions to that equation, different equations, and yet the solutions are closely related. The solutions all relate by way of a single fixed solution to the purple equation that I pulled out of thin air. And that's a really interesting fact. It's a relationship between things that are not immediately obviously related. So, very interesting result. And side note, it is also going to turn out that this will end up being computationally very useful to us later in the course. Just not right here at the moment. So I do want to show you in practice, well, you know, what this would look like directly applied. And here you go. So here's a system of equations, and you can check a couple of things. One is if you were to turn all of these numbers here into zeros, right? And if you were to row reduce to find the solutions, which would be the homogeneous solutions because we've put all zeros there, then these are all of your homogeneous solutions, and something you can just directly confirm. Okay. On the other hand, you can also confirm by simply arithmetic is that is a solution to that system. Now, it's not the only solution, certainly, but it is a solution, and this is what I'm just going to arbitrarily choose to call my particular solution. And what we conclude then from the statement of the theorem is that the complete set of solutions is that one particular solution plus the complete set of all homogeneous solutions. That will give me all of the possible solutions to the system.